Okay, my goal today is to finish off 3-4. So that's essentially 3 days on one section. So I wish I had more time. I would do 4 or 5 days on these, but you know, we have to move on. So my goal is to finish this today. And for Thursday and Friday, we'll be using or finding out about implicit differentiation. This is, in my opinion anyway, one of the most important rules you're going to learn. So, what kind of chain rule questions are we going to look at today? Well, we're going to look at quotient rule ones. Here's 4 questions that use the quotient rule with a chain rule. We're going to look at repeated use of the chain rule. So these are functions that we're going to differentiate that aren't just a chain rule, but a chain rule inside a chain rule. I sometimes call them Russian doll questions. And then I've tagged on a couple of unusual trig ones that I don't think are that obvious. So I put them in, and the 2 examples of them are 19 and 27. So let's get started. I'll pick a version of 12. And since we're going to be using the quotient rule, I'll put the formula over here just to remind us. And it's f dash j take away f of g dashed and all over g squared. Now the quotient rule is much uglier, it's more complex than the product rule. And the style points that we're going to have to deal with at the end, and they are going to be more significant, right? You're going to have to do a lot more work to get the thing into a format that's considered as nice as it can be. So here's our first question. If you see a fraction anywhere, in this case, x over x plus 5, you see a fraction anywhere, you're going to be using the quotient rule. Right? But sometimes you have to figure out, is this the best way to do it? What do I mean by that? Well, I'm going to split this thing up into 2 separate square roots. The top guy is going to be called f, and the bottom guy is going to be called g. And then we can find the derivative by f dash g, take away f of g dashed, all over g squared. Are you comfortable with the square root of a fraction becoming fractions with square roots? You know, that's algebraically, you're allowed to do that. Now, when you get ugly ones, like this, I have to rewrite them as fractional powers because I'm going to have to differentiate. And we can't differentiate square roots, but we can differentiate x to the half. So over here, I have got f, and its derivative is now a power rule. 1/2 x to -1/2. Just leave it alone. Then we're going to have g, which is x plus 5 to the half. We're going to differentiate that. Technically, this is sort of a chain rule, right? The inside function is just called x plus 5. So that's my inside function. Multiply by the power, reduce it by 1, and then you finish by multiplying by the derivative of the inside function. But since the inside function is just x plus 5, when you differentiate that, you get 1. So you can see in this case, it's almost like it wasn't there. Right? Because times 1 doesn't do anything. Right, so these are the building blocks that are now going to we put in here. So it's going to be 1/2 x to the -1/2 times untouched g. Take away the untouched f, and the derivative of this guy is 1/2 x plus 5 to the -1/2. And the whole thing is going to get divided by g squared, which is this guy squared. And that's calculus finished. Everything from this point onwards is style points, and it's algebra, which means we are going to make it look as pretty as possible. And we're going to start by looking for common factors on the top. And while I'm thinking about common factors, let's take care of this guy in the bottom. X plus 5 to the power 1/2 when you square it. Well, when you take one power and raise it to, in this case, a square, don't you just multiply them together and that gets you 1. The net effect is that the bottom is actually quite nice. Okay, like a square root being squared, right? They cancel out, you just left with x plus 5. Now, the hard part. Forget about the bottom guy. We've taken care of him. Let's just focus on the top. Common factors. There are two different pieces. There's this messy expression, take away this messy expression. I need common factors. Just tell me any one you can see. One will do.
X plus 5.
Okay. Now you have to decide -1/2 power or +1/2 power.
Negative half power.
Yeah. As weird as that looks, that's the right one to pick. Okay, look for another one now.
X to the -1/2.
Okay. Is there anything else that's a common factor? Because I can see one more.
1/2.
Right. Now, these are the really weird common factors. We've seen them a couple of times, but no matter how often you see them, they still look weird to me. So I do a bracket, and now it's what's left over. 1/2 is used up. The x to the -1/2 is used up. I have an x plus 5 to the 1/2, and I'm going to take away a -1/2 power from that. So I have a 1/2 power, and I'm going to subtract -1/2. What's the net effect? What do you get when you do that?
1.
Right, and x plus 5 to the power of 1 is just x plus 5. That was nice. Okay, now let's look at x to the, where's the other guy? Yeah, let's look at it over here. 1/2 used up, x plus 5 to the -1/2 used up. We have x to the 1/2, right? Take away -1/2. And what does x to the 1/2 take away -1/2 get you?
X.
Right? X to the power of 1, which is x. Well, that's, to me, that is the hardest bit. It's not easy what's coming next, but that's the hardest bit. So I am going
Is
to
that
try.
supposed to be -x or +x?
Oh, it should be -x. Well done. Yeah, because there's this here is a minus, so that's a minus. Right. I'm rewriting x plus 5 again. This -1/2 is going to come downstairs as +1/2. This -1/2 is going to come downstairs and be +1/2. That 2 is going to come downstairs. X plus 5, take away x, leaves me with 5. So do it again. 2 comes downstairs. -1/2 comes downstairs. +1/2 comes downstairs. And this here just ends up being 5. x to the half is now going to be called the square root of x. X plus 5 and x plus 5 to the power of half, when you multiply those together, can't you combine them into a single power of x plus 5? So that's like 1 power, and that's like another half power. So that would be x plus 5 to the 3 halves. And now we're finished with this last line. 2 square root of x. 3 halves is a square root of x plus 5 cubed. That's our answer. I don't know, 80–90% of the work we did here was not calculus. It was pure algebra, factoring weird powers, combining terms, making them look pretty. Any questions about that one? To me, it's the kind of question you have to go back and just study and, you know, look at it again, right? Now, the next question that is of that type is g of u cubed take away 4 over u cubed add 4 to the power of 8. Now, this one was the square root of a fraction. This is a fraction raised to the power of 8. Now, you can actually do this 2 different ways, but the way I would do this one is very similar to that one. Right? It's okay to break this up into 2 distinct fractions, because when I write it like this becomes f, and this becomes g. So we can use quotient rule. So this guy is going to be f dash g, take away f of g over g squared. So I do all the pieces now. The top is f, and it's u cubed take away 4 to the power of 8. So that's a chain rule. So its derivative is, so this is the inside function, 8 times u cubed minus 4 to the 7 times the derivative of the inside function, which is that guy. And so f dashed ends up being 24 u squared u cubed take away 4 to the power of 7. G is almost identical to it. It's that guy. Again, this is the inside function. So we're going to get 8 u cubed plus 4 to the 7 times the derivative of the inside function, which is also that guy. And so we're going to get 24 u squared u cubed plus 4 to the 7. So the f and the derivative, the g and the derivative, I've done these at the side. Now I'm going to plug them into here and make everything hopefully look pretty. So what do we get? We have f dashed, which is 24 u squared times this guy, multiplied by g, which is this guy. Take away untouched f, which is this guy, times g dashed, which is this guy, the whole thing is going to be over g squared. So we're going to take a u cubed plus 4 to the power of 8, and we're going to square it. What will this expression in the bottom be as a single power? So I've got u cubed plus 4 to the power of 8, all being squared. What single power does that become?
Power 16.
Right, 8 twos are 16. Now, there's an awful lot going on in the top. There's essentially two things. There's this bit, take away this bit. And it's the same kind of process as we've done with the square roots, in a way, probably a little bit easier. Find some common factors for me. And there's quite a lot going on.
24u squared.
Okay, agreed. Any other factors? Anybody see some more? Look here, look here. If they have the same thing, it's a common factor. I can see two different ones.
U to the third minus 4 to the 7th.
And the reason you chose 7, which is the right one to pick, was
It's the
you
lesser
could have
value.
picked 8, but why'd you pick 7?
It's a lesser value that does not have any issues.
Right, that'll work. What's the other one? Because there is one more, isn't there?
The u cube plus 4 to the 7th.
Now, at least there's no weird negative a half floating about, right? It's easier to deal with when everything's whole numbers, right? So that's why I said this is a little bit easier. Right, so these are all the common factors. So all we need to do now is find out, what was left. So used up, yeah. Used up, yeah. Used up, yeah. Only 7 of these used up. So does it not leave a u cubed plus 4? Are you happy about that? When you look at these terms and take out this, you're left with a single u cubed plus 4. Take away. Right. 24 used up, u squared used up, that one's used up. Only 7 of these. Why am I putting a bracket round u cubed minus 4? Why am I just not writing minus u cubed minus 4?
Because the negative distributes through the whole thing.
Right, so the brackets is to make sure I remember to do that. So we're pretty much finished here. We've got this guy. You've got this guy. There's still an extra bit, but we're pretty much finished. That guy, take away that guy. 4 add, you just get 8. That's nice. Two things happening here. The first thing, that when you put these together, they essentially cancel out and leave an 8, and you've got a 24 over there. So those can be combined, and 8 times 24 gives me 192. And I have a u cubed minus 4 to the power of 7. Do you notice that this u cubed plus 4 to the power of 7 and this u cubed plus 4 to the power of 16, they're the same thing? So shouldn't I be able to cancel some of these with that?
I had a question.
Yes.
So you wouldn't add 8 to 24, you would multiply it together?
Yes. Everything here is something times something times something times something times 8. So everything's multiplied. And so 24 times 8, not add. Yes. Right, if you don't see a plus sign and you know it's from factors, you know that one thing's being multiplied. Pretty much what it is. Okay, how's this going to work? What are you going to get left on the bottom?
U cubed plus 4 to the 9th.
Right. There you go. Style points, done. Pause that for a second. Are you okay with the multiplying? Does that make sense to you, Vanessa? Okay,
I think you left out a u squared.
I did, didn't I? I was just careless. Yeah. Are we good now? Right. Now, quotient rules, pain in the butt, ugly, no arguing with that, messy, every word, description, adjective you could do, but necessary, right? You've got to be able to deal with them. 16's one, let's do 18. E to the ugly power. Emphasize it. You want to differentiate this guy. You got to just deal with it. If it was e to the 2z or e to the x or e to the 4x plus 1, whatever it was, your answer would be e to the z over z minus 7. And then you would finish with the derivative of the inside function. Now, in this case, isn't the inside function a fraction? Which means then that here is going to be the derivative of this guy. So when I say times the derivative of the inside function, I'm really saying times the derivative of this. So we now have an f on top, a g on the bottom. Let's do its derivative. Actually, it's not that bad a derivative. I've seen worse. So it's f dash g, take away f of g dashed over g squared. If you differentiate that, you get 1, you leave the g alone. Take away, you leave the top alone, and you differentiate z minus 7, which just gets you 1. And you have the bottom squared. And this is z take away 7, take away z, all over z minus 7 squared. And that becomes negative 7, because they cancel out, over z minus 7 squared. So we go back here, and we get our answer to the original question. F dash z here is going to be e to this ugly guy, excuse me, times that. If I was wanting to try and make this slightly prettier, I might write it like this. But that's about all I can do. So there's our answer. Excuse me. Are we okay with this one? A weird e to the power using a chain rule followed by a quotient rule. Well, we've got 2 more topics to look at. One is repeated use of the chain rule, and then some unusual trig functions. So, 22. Let's look at that as an example of repeated chain rule. So, we've got a function. Oh, I'm just going to call it f of x. They've got weird letters on them. I'm not going to do it. Tan squared of n times x. I've just done that in the x's. To be able to do this question, you have to realize that tan squared x means that. It means tan of, in this case, nx squared. So you want to differentiate it. The inside function right now is the tan of n times x. So if you want to differentiate it, you get 2 times the inside function to the power of 1 times the derivative of the inside function. Right. Now, if that was tan x, wouldn't the answer be secant squared x, right? The derivative of tan is secant squared. Now, technically, isn't that the inside function for tan x? Why is that going important? Well, let's see what happens. If you differentiate the tan of nx, you get the secant squared of nx times the derivative of its inside function. And what is the derivative of nx with respect to x?
N.
Just
And
n. And then you make it look pretty. So there's going to be a 2, there's going to be an n, there's going to be a tan of nx, and there's going to be a secant squared of nx. And my nickname for these kinds of questions is Russian doll questions. You know those dolls where there's a doll inside a doll inside a doll? They're kind of like that. Doesn't help you do the question, it just makes me think, okay, there's a thing inside the thing, right? Suppose I gave you e to the power of the sine of 6x. You want its derivative. This guy here is technically your inside function, so it's e to the sine of 6x times the derivative of the sine of 6x. Forget about where it came from, just say, okay, times the derivative of the sine of 6x. Well, if you differentiate the sine of 6x, don't you get the cosine of 6x? But isn't that an inside function for the cosine? So don't you finish with not just the cosine of 6x, but the derivative of 6x, which is 6. So in this case, you get 6 cosine 6x e to the sine of 6x. And that's similar to 28. Right, next one I'm going to show you that's this Russian doll, right? Chain rules and side chain rules. Is a head scratcher. I like them because they're nice puzzles. We're going to do the sine of the cos of the tan of t. That's like 3 Russian dolls inside each other. So we have to keep our wits about us. As long as we do that, it's okay. We're going to find the sine of this guy. So this is my inside function. So if you differentiate the sine of someone, you'll get the cosine of it. So here's the cosine of the inside function. Followed by the derivative of the inside function. Wouldn't normally do it this way, but I'm trying to take it slowly. So we have the cosine of this guy. And these are not sine times cosine times tan. This is the sine of the cosine of the tan of something, right? It's a function inside a function. Now, I want to differentiate the cosine of tan x. So you can forget about what's going on around it and just focus on this. What do you get if you differentiate a cosine?
Negative sign.
So we're going to get a negative sine of the inside function, right, times the derivative of the inside function. And what is the derivative of tan x, tan t? Derivative of
Secant squared t.
Yep, secant squared t. And that's it, finished. It's just a matter of putting it together. There's a negative, I think, secant squared t followed by the sine of tan t followed by the cosine of the tangent of t. Now that's what I call a weird function. Would you agree? That is a function inside a function inside a function. And I know it looks really weird, but if you think about it, there is a logic to where the answer came from, right? It's just repeating the chain rule of a chain rule of a chain rule. Which now takes us to our last topic, unusual trig functions. Question 19 is an example of an unusual trig function. So g of theta is 7 times that guy. Well, if I want to differentiate this, you have to think of it like that. And if you think about it as 7 cosine of thetas, to the power of 4, it might make the chain rule a little bit easier to deal with. Because essentially it's a power rule, isn't it? So we're going to do multiply by the power of cosine theta and reduce it by 1. And then you finish with the derivative of the inside function and the derivative of cosine theta. Anyone want to tell me what the derivative of cosine theta is?
Negative sine theta.
And then all you do is, from the simplest looking thing, and then you can return that back so it looks more like the original. Are we okay with that weird one? So if you want to do sine cubed tan to the 10th power, right, that kind of thing, write it like this first, and then it's the chain rule's a little bit more obvious. And 27. Okay, so what we got here is the tangent of a square root of 6. Do you see a Russian doll question here? Because I see that, right? I see a function inside a function kind of thing. So take this one slowly. The inside function for the tangent is that, right? So the tangent function, this is its inside function. So when you differentiate the tangent of this guy, you get the secant squared of this guy times the derivative of that guy, right? And that's a little bit ugly. So when I see things that I think are a bit messy, I kind of go over to the side and I say, okay, I want to differentiate you. What would be the first step in trying to differentiate this function? Don't really care where it came from right now. We're just focusing on it. What would be the
as the square root of 6 plus the square root of tangent squared?
Oh, no. I thought you were going the right way there for a second. Oh. We are focusing only on this guy. So no tangents. How could you rewrite square root of 6 plus t squared?
Would you do square root of 6 plus square root of t
squared? I wish that was true. Do you know, math would be so much easier if that was allowed. And it makes sense, because if someone went and said to you 6 times t squared, you are allowed to split them, aren't you? but you're not allowed to do it when they're added. I wish that was true. That would have been exactly what I would have done. So here's my clue. What power of 6 plus t squared is a square root?
1/2.
Yeah. Isn't that how you, if I said to you, differentiate the square root of x, you wouldn't leave it as the square root of x. Wouldn't you have to turn it into x to the power of half before you could do it, right? Okay, so if you differentiate this guy, you multiply by the power and you reduce the power by 1. But doesn't this also have an inside function? So it's a chain rule, isn't it? So 1/2 the inside function to the power of negative half times the derivative of the inside function, which is 2t. Now a half times 2 cancel out. You've got a t. This guy is a negative power, so he comes downstairs. And this guy ends up looking like the original. There. So the derivative of this square root is that guy. So I can now go and put it in. And it's going to be t over the square root of 6 plus t squared. I really can't see much improvement to that. I guess I could stick them together as a single fraction, but it would, yeah, it would look ugly no matter what you tried. Well, that's almost all the chain rule stuff that we have time for. You're going to find that there are many, many different combinations of functions that end up being chain rules. So you have to just be open to, you know, take each one on its own and figure out how it's going to happen. I'm going to show you a really cool question. Which I am stealing from one of our professors, Elizabeth O'Neill, who likes to use this question when she does her calculus. This function is e to the power of e to the power of e to the x. This is definitely a Russian doll question. You have got 90 seconds to find that guy's derivative. From now, go for it. Time. Okay. This is a Russian doll kind of question going crazy because we've got powers inside powers and so on. Anybody want to have a shot at it? Anybody feel lucky?
I feel lucky.
Go for it. What you got?
So, I got e to the power of e to the power of e to the power of x. Then basically that same string of numbers minus one of the e's. And then that again minus one of the e's. And then, yeah, that's it.
That's it. Isn't that a kind of pretty answer once you see it? There you go. You nailed it. Well done. I'm not doing, I think she does 3, but she might have done 4 E's. But if she did 4 E's, wouldn't it just look very similar? Right. So while I'm doing the next little thing, why don't you put your name down, and I want to show you what we have on Canvas and talk a little bit for the last 5 minutes about, you know, your midterm. So 7 till 9. What do you need to know? I'll click on that one in a few moments. If you click on this one, here is the link that you'll use. So it's not your class link, pardon me, it's not your class link. This is the link that you'll use to join the class. You need to have your camera on. I need to see you guys. Somebody in my other class says that you can get a webcam in Walmart for under $30. I think he said 15, but don't quote me on that because it could have been 25. But it's definitely under $30. So it's not hopefully too expensive for you, but you need one. If you click on that, this is Microsoft Lens, and this is a video how to use it. If you don't have something on your phone that's already from a previous class, I don't care which software you use, but you will have to do all your working on paper and show me what you did to get your answers. So it's not going to be in WebAssign. There is no exam on WebAssign. It's not like an online test. It's done in Canvas. You will find it here when Monday comes. When you finish your working, which will be, what will that be? It's 7. That should say 9:30. Huh. Okay, I'll fix that. Anyway, once you've finished your test at 9, you have until 9:30. So I will fix that to say 9:30. But just to remind you how that works, you click on that, you do this guy, you upload your file, you choose a file, you pick the guy you want, and submit. So get practice at using it. It doesn't matter what you upload, because when you upload your working, whatever's there gets rubbed out and the new guy takes over, right? So if you want to just get practice, you know, uploading, I don't know, your English homework or something, just for practice, right? So take pictures, check them out, upload them, and that will be it. When you're finished your midterm and you've uploaded it, there's a great temptation to you say, I'm out of here. And will you not do that yet? Once you've uploaded it, will you tell me? Because what I'm going to do then is I'm going to go in and look. And very often, there's not a problem, and bye-bye, you're out of here, right? So if you finish early, you're finished. But sometimes you miss a question, and I'll scan through it and I'll say, there's no question 7, did you just not do it? And that's fine. No, you'll go, oops, I missed it. So here's the little problem. If you miss a question, you have to upload the whole thing again, because the way this works is it rubs it out. So if you only show me question 7, it'll rub out the other 9, right? So you'll got it. So anyway, that's it. And the second one, which happens very rarely, but it will happen to about one of you, it's so faint I can't read it, in which case I'll ask you to do it again. So make sure that when you're finished, that I have a check and I tell you everything's good to go. And then once that's done, you are fine. Down here, you get a midterm practice. So it just gives you some examples of what your midterm look like. And when you're doing the working and uploading it, try and do as much working as you can. I know in homework, perfectly understandable, you might cut some corners, but I can give partial credit if the method is right, but I have to see all the working to know that you're doing the right method. And then let's look at this guy. All right, there we go, 9, that works. Here are the topics. Do you notice that there's one topic 2, 4 missing? Remember that, what was it, 3 or 4 question thing, the formal definition of a limit, the delta and epsilon stuff? There is no question in that, so you don't need to worry about it. Here are the questions. You can pretty much guarantee that there's going to be one question from every section. We've finished the chain rule, so tomorrow and Thursday we'll be doing implicit. You are allowed any physical notes that you've written down. WebAssign will disappear on the day of the midterm. So if you go to WebAssign, none of your homework will be there. Actually, nothing will be there. So when you go to Canvas, all the videos and all the help pages, they will all have disappeared. So the only thing that you will see is that one module that has all the stuff that you need to do your midterm. So that means you have to make sure that you've got all the notes that you want already done by midnight Sunday. Little note here. I'm not testing, can you write down every question in the universe, write it down with 400 pages of notes, and then every time I give you a question, you don't know how to do anything, but you know how to go and find a question like it and just copy it. That ain't going to happen because you only have 2 hours. And if you have to go hunting through a whole load of notes because you haven't memorized anything, I say to you right now, what's the derivative of tan x? You should be able to say secant squared x. If every single thing you have to go and look at a note because you haven't memorized anything, that will slow you down and you won't have time to finish the test. So there are just some things you've just got to know. You got to know the product rule off the top of your head, right? You got to know the quotient rule. You got to know the power rule. And you got to know that the derivative of secant x is secant x tan x, right? That's what makes a good mathematician. And I've not got the best memory in the world. Now here's the last thing I want to mention for today. There are no extensions. Week 5, midnight Sunday, the door closes. No homework is going to be accepted after that point. So you will have to catch up with any extensions because some of you have extensions from last week, which means you now have 2 weeks homework to do in one. You got to get your online test done because that's week 5 finished. We move on. And so you make sure that you understand that. Don't send me, can I have an extension? No, I'm not treating anyone different from anyone else. Nobody's getting one. It's finished. That's 5 weeks over and we are good. And good luck. Tests are stressful. So don't be too cruel on yourself. As long as you've done the best you can, that is great. If you've done the homework and you've been, putting in due diligence, you won't be too many shocks in the midterm. You should be able to say, I've seen things like that in the homework, or he did questions like that in class, right? So there shouldn't be, what the heck is that question? I've never seen it in my life before type of question. Of course, chain rules kind of look like that, don't they? Because they all are so different from each other. You might say, well, I haven't seen one like that. Well, that's maybe possible, but it's still a chain rule, so you know how to do it. Any questions?
Are we supposed to Sorry. Are
No,
you supposed to print off the midterm and write on like
No,
the
don't need
question?
to print it. No, you can just read it from the screen, right?
And
So
then put like a number next to it in the process
Yeah.
and the answer.
yeah, can I give you an example? Suppose this was your midterm, right? This is a practice one, but let's pretend for a minute it was your midterm. If it was a multiple choice, you would just say, question 1, the answer's C. Question 4, E, right? And then you get to the section 2 stuff. You would say section 2 at the stop, and then you would say question 1, A, and show me all the working. B, show me all the working. In this question here, wouldn't you just write 4, 0 does not exist? In this question here, you would show me the working for the limit. In this question here, wouldn't you be drawing what the derivative looks like? Don't know why I put spaces there, because you don't need them. But here you would find derivatives, and this big bunch of questions is all about different kind of derivatives. And I was going to say here's a chain rule, but evidently I don't have a chain rule. That's weird. Oh, I do. There we are. There's a chain rule. Actually, so's that a chain rule. So you will show me the working, and then you use that software. Basically, you take pictures of everything that you've done, all your working, including the answers. People can make my life easy by numbering the questions clearly and maybe putting a circle around the final answer. And remember, unlike WebAssign, you do get partial credit. So if you do a really horrible question, like maybe a chain rule question, and you dropped a 2, right? There was a 2 there and you lost it. If you did 90% of it right, you'll get 90% of the points, even if the final answer is wrong. Where in WebAssign, if the final answer is wrong, isn't it just hard luck? You've lost all the points. So working is important. If I don't see working, I'm going to assume that you cheated and I'm giving you 0 points. And it's no good you saying you did it in your head, because that ain't an excuse I'm going to accept. If I can't see working, you didn't do it the way you should do. Now that is for questions where that makes sense. So all these questions here are working. On the other hand, if I asked you to draw a sketch of this function, would you agree there's no working? You just draw a picture, right? If I asked you to do a multiple choice, isn't the answer just going to be B? I don't need to know working, right? Would you agree in question 3 there's no working? But in question 2 there is, right? So it's pretty obvious what questions you can show me working for and which questions are just answers that you write down. Which is a long-winded question, but I'm glad I answered it that way. What you got? Any more? Okay, I'm going to keep this part inside this video. So if you want to, you go back and say, what did he say about, what you can and can't do? You'll find it there.